11, you can start. Thank you.
Can you see my screen?
Yes.
Good. All right, so good morning, everyone, or depending on your time zone, good afternoon, good night. Welcome back to the second lecture. Just for your information, Thiago posted both the video of my first class here and also as an attachment the slides related to the first part. And today, by the end of the class, I'll email the second part of the slides. So I want to start the lecture by asking if you have any questions from the previous lecture. No? Okay, so just a quick recap. We were considering the scattering problem where we had initially a plane wave inside on a scattering center. And this was a very complicated problem. We had to find out if we wanted to solve this problem, we had to find out what's this wave function here that has a piece that's a plane wave, and there's the scattering part that's related to spherical waves. So we said, what can we do to make the solution to this problem easier? We did some hypotheses related to especially to the spherical symmetry of the scattering center. And then after some math, we got to the point that we said, okay, instead of solving that complicated problem, let's look at something simpler, which are these phase shifts, which is the difference between the solution without the potential and with the scattering potential. And we argued that the only thing that could happen outside of the range of the potential was a phase difference between those two solutions. So we reduced that complicated problem to actually finding out phase differences. This isn't a simple task. So we looked at some other limits, the low energy limits, where we could reduce the problem of finding, this phase shifts by just calculating a number. So those phase shifts in the low energy behavior, they are described by this number, the scattering length. And I told you that today I'm going to talk more about this quantity, but we had some motivation related to the reduced wave function of what this scattering length means, okay? So any questions? No? Okay, so moving on for today's first topic, which is another quantity that also has the dimensions of length and related to this problem, which is called the effective range. So that expression that related the phase shifts to the scattering length, another name for that, it's the zero range expansion. And why is that the name of that expansion? Is because we were considering the force, the scattering center to have, we are not considering the range of that scattering center. So what happens if that quantity, the range of the potential, is small, but it's still non-negligible? What do I mean by that? Is that the range of the potential is much smaller than the scattering length, but still it's not zero. So what approach can we take to that expansion that we had? So we had this expression here, and to the right, there was only the scattering length. So we can think about expanding this quantity here in powers of k. We've got the first term, which was -1 over the scattering length that has no powers of k. This function is an even function. So k is an odd function. Cotangent of the phase shift is going to be an odd function. Their product is an even function. So this series in powers of k can only contain even powers of k. So we can try and find the next term in this series, which would be proportional to k squared. I'm already showing the results. So far we only got this. Now I'm going to get this piece here that goes with k squared, okay? But still, we are going to neglect higher k components. And remember, we are in the low energy limit. So k squared is still a small quantity. Is it clear what we are going to do in the following?
Yes, it's clear.
Okay, thank you. All right, so some math now, bear with me. Remember that we wrote the wave function outside of the range of the potential like this in the previous slide. So I'm writing it as a function of the phase shift and as sines and cosines, okay? Now I'm going to take two solutions to that differential equation that I wrote earlier with different energies. And if there are solutions, they obey that differential equation that I had before. And I'm labeling those solutions by K1 and K2 related to those two different energies, okay? So I'm picking two solutions with different energies, and if there are solutions, they obey those two differential equations. And what I'm going to do, I'm going to multiply the first one by the solution with K2. I'm going to multiply the second one by the solution with K1. And then I'm going to subtract one equation from the other, okay? So I'm just doing that. If I do that, you can see that some terms cancel, especially those with the potential. That's the main trick here. And then I just have this equation here, which contains both the function and the second derivative for the two energies, K1 and K2, okay? We can borrow this from calculus 1, and then write this difference that has a second derivative and the function as the derivative of something that has just the first derivative and the function, okay? So this is just a calculus identity, nothing deep or physical about this. I'm just rewriting those equations, okay? Next, what can I do? I can integrate both sides of the equation from 0 to capital R. Remember that capital R is the range of our potential, okay? So on the left-hand side, I have the integral of the derivative. That's just the function evaluated at R equals 0 and R equals capital R. And then on the right side, I do have this integral that I have to do. And of course, the energy of the particles doesn't depend on R. I can take it out of the integral. And don't worry, the integral converges because, as you remember, the radial wave function is related to the reduced wave function, dividing it by R. And since our boundary conditions are that at R equals 0, this is 0, we won't have problems as to dividing by 0, for example, in this function. So we are safe in that regard. Okay, so I got this equation by considering those two solutions with different energies. I can do the same thing if I consider the free case, the case where I don't have the potential in my differential equation. And the result is exactly the same if I come to this expression and replace everything that's U by G, G being the solution for the free particle. Okay. I know it's a lot of math. I'm not done yet, but so far, any questions?
No.
Okay. So I'm going to take another difference now, which is the difference between the free particle solution and the solution with the potential, okay? So it's just subtracting two equations like those from the previous slide. One has the free solution, which is G, and U is the one with potential that's different from 0. Okay. I can substitute the boundary, the boundary condition that I used before. I can use the fact that outside of the range of the potential, the free particle solution and the scatter solution are the same. So that's going to cancel a bunch of terms. I can substitute the functional form of the free particle solution. Okay. If I do all of that, I get this equation that I probably wrote on the next slide. Yes. So I get this one here. And you can see that now this is kind of looking like the thing that we had before. We had k cotangent of delta equals something. That something was 1 over the scattering length. So here we are almost there. So just one more step. We can take, I said that we are considering solutions of two different energies. We can take one energy going to 0. If we do that, you can see that this here I can substitute by 1 over the scattering length, which is what we had before. I'm dropping the 2 index, the 2 label from this other solution, so that I get this expression here. And then from here, I can define what's the effective range. I can look at this integral here and say, in the low energy limit, this is going to be the next term in this expansion of powers of k, because I have my k squared here, so this is the next term. And what's the effective range in practice? It's going to be this integral here, which is the difference between the square of the wave function outside of the range of the potential. We saw earlier that this only depends on the scattering length, minus the square of the wave function inside the range of the potential, which is going to depend, of course, on the particular choice of the potential that you want to compute. Okay, so a lot of math, but the main message here is the following. I have to first solve the free particle problem, and then I get some solution, 1 minus r over a. And then I have to solve the problem that we want with the potential that we want. And that's going to give us another solution. Then based on the difference of the squares of those two, I get a number, which is the effective range, which is this next term in the expansion. Okay, so by looking at the solutions with and without the potential, I can get two quantities. I can get the scattering length and the effective range. And both of them give me this behavior of those low energy phase shifts. Okay. If I look at this expression doesn't say anything particular about the shapes of the potentials that I'm considering. I can have two different potentials with very different shapes, but if they have the same scattering length and effective range, they're going to give me the same phase shifts. So just illustrating, I could have some potential, I don't know, that's a square well here, and I could have, I don't know, some Gaussian potential, something like this. They're very different in shape, but if they give me the same scattering length and effective range, they're going to give me the same low energy properties, considering this scattering. Okay, so sometimes this is also called shape-independent approximation because of that. So the shape parameters are going to appear at higher orders, but here I can do everything without worrying about the particular choice of potential in my problem. Does that make sense?
Could you repeat that? Sorry.
Which part? The
What is it
the
called?
interpretation of the scattering length and effective range?
Yeah, please.
Yes, okay. All right. So we reduced our problem to computing those phase shifts. And we related those phase shifts to two quantities. The scattering length that we saw yesterday, and today we saw a new quantity that also depends on the different wave functions of the free and interacting case. And they appear in this expansion of the phase shift. Notice that what appears in this expansion is the scattering length and effective range. It's not saying anything particular about the shape of the potential, how the potential looks like. So I could think about this particle being attracted to the origin by a square well. So I'm going to draw a square well like this. All right, so it has this shape of a square well. And I could compute the scattering length and effective range for this square well. Then I'm going to consider a different potential of a different form. The example that I used, it was a Gaussian. So I'm going to draw a Gaussian here, which is very different in shape from this other potential. So this is one V of R. This is a very different V of R. Now, if this potential has the same scattering length and effective range than the previous one, they give me the same phase shifts. So this expansion here doesn't care about the details of the potential, only cares about these two quantities here. So this expansion here is sometimes called shape-independent approximation, which means that we don't care about the shape of the potential. As long as it gives me the scattering length and effective range that I'm looking for, that I want, that's fine. All potentials of different shapes, they're going to give me the same scattering length. Shape corrections based on the shape of the potentials are going to appear in those terms here, higher order terms. Is that better?
Yeah, it's very clear. So this is sort of an effective field theory for potential, and those would be the low energy constants, in a way.
I mean, you can draw a parallel between those two, sure. But here I'm not talking about field theory. I'm not talking about low energy constants. Sure thing, you can fit an effective potential with low energy constants to reproduce some scattering length and effective range that you want. Sure thing. But that would be the connection between the two things, right? So you can, if you have two low energy constants and you say, I want to fit those to the scattering length and effective range, that's fine.
All right, thank you.
Okay. More questions?
I have a question.
Yes.
Thinking about in the validity of this expansion, when
Yes.
the higher terms will contribute, when these shape-dependent terms will contribute, because I have some difficulty to understand. This is a expansion valid in a low energy limit.
Yes. So
Yes.
this is valid in the low energy limit. So as you can see, this is a series in powers of k, right? So that's why the first term didn't have any powers of k. It was just related to the inverse of the scattering length. This second term here has k squared because we want to consider finite ranges, right? So what we did yesterday, where we said something like, oh, this is the low energy limit, right? The product of k times the range of the potential has to be small. If I consider my range of my potential being 0, so a delta-like potential, what do I get? I get the first term of this expansion. I stop here because k, because R0, the product here is 0, right? Now, what we did today was, okay, K doesn't have to be 0, but it has to be small. Or the range of my potential has to be small, or better yet, the product of those two has to be a small quantity. What's the next term that I get? Get this one here. And we could keep doing that and getting the higher order expressions. So that's the validity. Today, if I have time, I'm going to show you, for example, if you have a bound state, how the bound state energy is related to the scattering length and the effective range. And that could be a criterion for you to see or to gauge how good this approximation is or it isn't in a concrete example. Because you can always solve, for example, for a two-body system, you can always solve the Schrödinger equation exactly. And you get some energy of the bound state energy. If you are in this low energy limits, you can also compute this bound state energy from those two quantities. Then the question becomes, is this low energy approximation good? Are the results the same? Do they differ? That kind of question can answer if those higher order terms are important. Does that make sense?
Yeah, a lot of sense. Thanks.
Okay. More questions?
Lucas, how can we
Yes.
measure the phase shifts experimentally?
Okay, so I don't do experiments. I'm a theorist, and you have like very different settings if you're talking about atomic physics, nuclear physics, particle physics. So I think I'm not going to answer this question, otherwise I might say something dumb. Okay, but the main thing is this is going to be related to the system that you want to measure. Okay.
Okay, sure. Thank you.
Probably next week you can ask some of the lecturers, and they will have much better answers than I would. Okay.
Okay, thank you.
More questions? But what I'm going to teach you how to do is to calculate the scattering length and the effective range for an arbitrary potential. By the end of my course, at least you know how to do that. Okay. So I've been talking a lot about bound states. Okay. So if we go back to that wave function that I've written a couple of slides ago, we can see that if we consider the S wave part, L equals 0, and look at the behavior of our scattering wave function, we get something like this. So we have an incoming spherical wave and an outgoing spherical wave, and that's multiplied by that S matrix element. Okay. So if we want bound states, we can look at the Schrödinger equation and look for solutions that are of negative energy because we want bound states. All right. Outside of the range of the potential, everything is easy because it's a free particle. And I think everyone here knows I'm defining kappa as the usual quantity that you're used to. And I think everybody knows that we get a linear combination of exponentials, a decaying exponential and a growing exponential. If we want a bound state, this piece here is not physical because that would correspond to the wave function blowing up to infinity at large distances. And this is the part that describes a bound state because it decays with R. Okay. So for any bound state solution, if we are outside of the range of the potential, what's the behavior of my radial wave function here? It's going to be this one here. So it's this vanishing decaying exponential divided by R. Okay. This is a result that you might have seen before. Okay, so let's compare those two situations. So if I have a bound state, we just argued that this is the solution that we get at large distances. And the scattering theory is giving me this here for the large our behavior of my wave function. What happens if I substitute the k that we had for the scattering states by I kappa, kappa being the momentum associated with the bound state? If we do this, so I have e to the ikr. I'm going to substitute k by I kappa. So I get e to the minus kappa r, or the same thing as a bound state. So if I take my scattering solution and substitute, allow k to be imaginary, purely imaginary, and substitute this, I get the same behavior of a bound state. How about this S naught here multiplying the outcoming spherical wave? It's controlling how much is going to the outgoing or incoming spherical wave. So if I only want this piece here to contribute, then I want this term here to be infinite. And I want this to go to the infinity. So I can disregard this other term here. Okay. So if I do that, I only get this scattering solution. So I have to do two things. I have to make sure that this S here, this S matrix element here is going to infinity. And I want to replace K by an imaginary quantity, right? So if this S here is going to be an imaginary function and it's divergent, that means it has a pole at K equals I kappa. So what I'm doing is I'm looking at this S matrix element and I'm saying, okay, if K is real, I have scattering. So this is going on this real axis here. So for K greater than 0, I just have my scattering solution. However, if I go to this imaginary point here, I kappa, I have a pole because my scattering matrix element is divergent to infinity. Okay. So I can write down my S matrix element, and I can use our knowledge of the scattering length. We related the S matrix to the scattering amplitude. That in turn, we related a few slides ago or yesterday to the scattering length. So if I do that, I get what my S matrix element looks like. And right now we can see where the pole is, right? The pole happens here when K equals I over A. But we said that we had to substitute K by I kappa, right? So this pole of my S matrix happens when my kappa equals 1 over the scattering length, okay? So that's the main result here. My S matrix element is going to diverge because it has a pole, and the location of this pole for a bound state is when the kappa of this bound state equals 1 over the scattering length. So how is that connected to the energy of this bound state? So the energy is k squared over 2m. I substituted k here by I kappa. So my bound state energy is proportional to minus kappa squared. And we just saw that kappa is 1 over A. So that's the result here in this zero range theory. If I have a bound state, the energy of this bound state is going to be proportional to 1 over the scattering length squared. So in this low energy limits, zero range theory, my bound state energy is determined by a single number, and that single number is the scattering length. Is everybody following? Do you have questions? Can I continue?
Yes. For me, you can.
Okay. All right, so far we only talked about one particle that was plane wave, and it was interacting with a scattering center at the origin. now I want to connect all these discussions that we had to particles, two-body scattering. So I want to connect this situation here to a different one that's just two particles interacting, one being scattered by the other. Okay, and you'll see that with very few modifications, we can apply everything that we derived so far to this problem. Okay, so I can write down the Hamiltonian for the two-particle problem, which is the kinetic energy of particle 1, the kinetic energy of particle 2, and the potential that they are interacting with, the interparticle potential. Okay. Now what I'm going to do is separate this in center of mass and relative coordinates. Okay. So I'm going to write my center of mass coordinates as being this. Of course, if we have equal masses, the expression is much simpler. And the relative coordinates are going to be the difference between those two particle coordinates. If I do that, I can break up my Hamiltonian into a center of mass piece and a relative piece. The center of mass piece is just going to be the kinetic energy related to kinetic energy of the center of mass. So that's just the center of mass is going to be just a plane wave solution, and it's just going to add a constant to my problem. So it's just going to be a constant energy to my problem. So we are not interested in that piece. We're interested really in the piece that describes the relative motion. So we can go to the center of mass frame where we don't have this movement of the center of mass and look just at the relative movement of the particles, which is this piece here. Okay. And in doing so, I assumed that the potential was spherically symmetric. Okay. So we can relate everything that we used before to this problem as long as we consider interactions that they don't depend on the relative orientation of the particles, that they depend only on the absolute value of R. Okay. If we go back and look to the equation that I wrote for a single particle, it's the same thing. We just have to replace everywhere where we had the mass of the particle. Now we have to replace it by the reduced mass of the two-body system. So everything that we did so far applies. We just have to go to the center of mass frame and substitute all the masses that we had before by the relative mass. Okay, and if we're talking about the same particles, they are equal mass. I just have to divide the mass by 2, so it's just a factor of 2 different. Is everyone following?
Yes.
Good. All right, so we talked a lot about general settings, arbitrary potentials. So right now I want to do some concrete examples so you get a feeling of how these results that we derived worked in real world applications, okay? So I'm going to start with something that I said a lot before, but now we are going to actually do all the calculations. So I'm going to start with an attractive finite well, spherically symmetric. First, we're going to consider scattering states, so the energy being greater than 0. And afterwards, we're going to see bound states. And I'm going to walk you through the calculation of the scattering length and the effective range for this case here. Okay, so that's the first application that I want to show you today. Okay, so I think everyone is familiar with the spherical well. Here I'm going to consider just the attractive case. So it's constant for distances smaller than the range of the potential, and then it's going to be 0 for outside the range of the potential. Okay, and probably you are used to writing the potential as I'm writing here in the first part of the slide. Where this capital V naught has units of energy, right? In the following, I'm going to write the potential in a slightly different way. And the motivation for doing this is because in tomorrow's lecture, I want to show you some numerical approaches to calculating these two quantities, the scattering length and the effective range. And for that, it's interesting to work with dimensionless quantities. So I'm rewriting this potential in this fashion here, so that this term here carries all the dimensions of our problem, the energy dimensions of our problem. And then I'm left with just one parameter that's dimensionless, okay? And we're going to consider only the cases where this potential is attractive. So this V naught here is positive. And if we have very shallow potentials, meaning that the potential is not strong, this is not going to bind the particles together. So then we have continuous scattering states. That's the case of the positive energy. But if I keep increasing this V naught, it's going to be attractive enough to form a bound state. And that's what we are going to do in the following. See how a bound state appears in this system. Okay, is it clear what we're going to do?
Yes.
Good. All right, so that's just solving the Schrödinger equation for this potential. I'm going to start with the scattering states, positive energy. Outside the range of the potential, my Schrödinger equation is pretty simple here. It's just a free particle. Inside the range of the potential, this is one of the simplest, if not the simplest potential. It's just the potential is going to be just a constant inside the range of the potential. And I just rewrote this constant to have these units just like momentum here, right? So this K naught here is just related to the two parameters of the potential. So I have to solve these two differential equations here that probably you've been solving equations like this since you took a modern physics course or quantum mechanics 0, okay? So what do I have to do? I have to get the solutions. Where is it? I have to get the solutions for those two differential equations. Inside the range of the potential, it's just sines and cosines. Okay. As I said before, the boundary condition for r goes to 0 is that the function has to vanish. So this term here is finite for r equals 0. It's 1. So I'm going to set b to 0. So I just have a sign inside the range of the potential. How about outside the range of the potential? Well, yesterday and today, we wrote this form here for the wave function outside of the range of the potential in terms of the phase shift. Okay. So I have that my wave function looks like this. Now, what do we have to do? We have to match the function and its derivative at r equals capital R, the range of the potential. If I do that, it's a little bit of math here. I'm showing it over here. And then I can solve for the phase shift. And then I get this expression here without any approximations, meaning this is exact for the spherical well, attractive well. This is the phase shift in terms of the potential parameters and also the momentum K. So you have K here, and R is the range of the potential. And inside this K naught here, remember, we have the other parameter of the potential, which is the depth. Okay. I know that's just math, but I just want to show you that even in this simple case of the spherical well, which is the simplest potential I can imagine, the expressions, the analytical expressions for the phase shift can be quite complicated. For more complex potentials, most of them, we can't even get those analytical expressions. We can do stuff like this, but we end up getting those phase shifts numerically. Okay. So far, any questions? No?
No.
Okay. Okay. All right. So I talked about generic solutions, and I didn't say anything about this being low energy, other than the fact that I use that functional form for the wave function outside of the range of the potential. But what happens if we take the k to 0 limits? Okay. So how do we do that? We go back to that equation on the last slide, and we take the k goes to 0 limit. Remember that we have to be consistent with our approximations. So I'm expanding the cosine and sine like this, right? I'm going to collect all the factors that appear of the product of k cotangent of the phase shift, because we can relate that to 1 over the scattering length, as you remember. And if I take that on this equation here, I get this other equation at the end, at the bottom of the slide. If I rearrange things, what do I get? I get an expression for the scattering length. So here is the scattering length A in terms of the parameters of my potential, my depth V naught, and the range of my potential R. Okay. So in this very simple case, we can write an analytical expression of my scattering length in terms of those two parameters that define my potential. Okay. Now, if you look at this expression, you'll notice that we have a tangent here. And the tangent diverges for some values of the arguments, right? Tan of x diverges to infinity for pi over 2 plus multiples of pi, right? And the first divergence of this quantity here happens when the depth of my potential is pi squared over 8, okay? So the message here is that this scattering length diverges for some values of the potential parameters, and that the first one that happens at this value of the depth. Okay. So far, are you following?
Yes.
Yes.
Good. All right. So we did the positive energy case. Now let's do the bound states. I could do all the calculations that I did before, now considering a negative energy. So just redo all the calculations up to this point. But I'm lazy. There's an easier alternative. Remember that when we discussed bound states, we said that we could take every result that we had so far and substitute k by I kappa, and this was enough to get a bound state, meaning that if I had some energy that was proportional to k squared, now I get a bound state energy proportional to kappa squared. So I'm going to do exactly the same here. I'm going to take the solutions that I had before and substitute whatever I had k, I'm going to substitute by I kappa, okay? So if I do that, I still get a signed solution inside the range of the potential. The difference now is that outside the range of the potential, we get that solution that we talked about a few minutes ago, where I had a vanishing solution, right? And this is consistent with us getting a bound state. I'm going to do exactly the same thing that I did before. I'm going to match the solution and of the wave. Sorry, I'm going to match the wave function and its first derivative at the range of the potential. If I get the ratio of those two things, I get this equation here. Okay. Again, just math. I invite you to work this out at least once to know what's going on. And after some manipulations, I get this equation here, right? That's not as easy as the case where we had the positive energy, the scattering states, because here this equation is transcendental, right? We have kappa appearing inside the arguments of this tangent here, inside that square root over there. So we cannot solve this analytically. However, it's very easy to solve this numerically. So if we wanted to solve this numerically, we just have to plot these two functions here and see where they intersect, okay? But even though we cannot solve this analytically, we can still get some information out of this equation. This term here is always positive, okay? So this term here is always positive because it's related to this kappa that is the bound state energy related to bound state energy. K naught here it has to be always greater than kappa, because if we go back, we'll see that it's related to something positive plus kappa. So this term here always has to be positive. So if I want this to be 0, we need this other term here, this tangent here, to be negative, okay? So if we want a tangent to be negative, we can write the intervals where a tangent is negative. So the conclusion is that the argument here of this tangent has to be between those two values, pi over 2 and pi, or pi over 2 plus pi, between that and 2 pi, and so on. So this argument here has to be between those two limits here, given by the fact that this is the argument of a tangent, okay? So where is the first bound state? That happens when n equals 0, meaning that the condition for this first bound state is this one. It has to be between those two values. Using this inequality here in our definition of kappa naught, just substituting those things inside this inequality here, what we get that the depth of our potential has to be greater than pi squared over 8 for a bound state to appear, okay? So the first result is that there is a threshold for a bound state to appear, meaning that if my potential is not attractive enough, if it's very shallow, I don't get any bound state. If I keep increasing the depth of my potential, at some point, a bound state is going to appear, and the threshold value for that to appear is this pi squared over 8. Now, if you recall a few slides ago, when I was deriving the scattering length for this potential, we saw that this value of V naught, pi squared over 8, made the scattering length diverge, right? Was exactly this value. So what's our conclusion? Our conclusion is each time the scattering length diverges, a bound state appears. So we have a situation like this. I'm plotting in this graph that analytical expression that we got for the scattering length as a function of the parameters of the potential. Here is whenever the scattering length is diverging. So at those positions here, the scattering length diverges from minus infinity to plus infinity, right? And each time the potential diverges, a bound state appears, okay? So if I begin with my potential being 0 or very shallow, the scattering length here is negative and small. As I increase the attraction of my potential, this scattering length gets more and more negative, more and more negative. It diverges to minus infinity, then it flips to plus infinity right after a bound state appears. And it's going to continue to do that, to decrease, and then change from minus infinity to plus infinity each time a new bound state appears, okay? So that's the connection, and it's easy to see in this analytical case, between the scattering length diverging and bound states. So for this shallow potential, I don't have bound states, and then they keep appearing each time the scattering wave diverges. Is that clear? Do you have questions?
I have a question.
Sure.
Why in the I don't know if I understand very well what in the spirit of this class, what is a two bounded states or three bounded states? How we deal with that in the formulation of center of mass or something like that? I thinking about something of mean field theory or just something about mean body theory or something like that. I don't know. But my question is about why uh, we see the the effective range is going down in the three bounding states. It goes up to zero. uh, I don't.
Okay. So let's try to do the following. I have my potential V as a function of R, and I'm going to take the range of my potential fixed. That's some capital R here, right? And I'm going to start with a very shallow V naught here, okay? So I have two particles, and they're going to be attracted to each other if they're at a distance smaller than R, or they will be free of each other if they're a distance greater than the range of my potential, okay? And first I'm considering this case here. So for this very shallow case, there's not enough attraction to overcome the kinetic energy of the particles. It's not going to bind the particles together. So I only get scattering states, right? One of them is going to fly by the other, and that's it. They're not going to bind to each other. So that's what I mean when I say there's no bound state. I have two particles, and they're not restricted to a finite region of the space. For this first example,
Okay.
is that clear?
Mm-hmm.
Yes, good. All right, I can keep increasing the depth of my potential. I can make it so that it's more attractive. And I can keep doing that until the attraction that I put in this two particle system is enough to bind those two particles, all right? And what we saw is that for this case where we can do analytical calculations, this has some critical value, a threshold. So pi²/8 in this case, okay? So in that case, those two particles, if I have exactly this pi²/8, they're bound, but their binding energy is negligible. It's almost nothing. I could say the binding energy of these two particles is zero, because I just gave enough attraction for them to bind, but the binding energy is so small that it amounts to nothing, okay? Of course, if I keep increasing the attraction between the two particles, then this binding energy is going to be some finite value. Okay?
Okay.
All right. So that's what I mean when I say that for this pi²/8, a bound state appears. Okay, so now the system supports a binding state of those two particles. All right. If I keep increasing my attraction, at some point, I'm going to allow a second bound state in my system, right? So if I write the energy diagram of bound states of my system, it's going to be something like, I have my ground state here below. I have a second bound state here. And then, so For example, the 0 could be here. So this is negative, so it's a bound state. This is 0, this is negative, it's a bound state. And above the 0 energy here, I have all my scattering states that are allowed, okay? So that's what I mean when I say I have a second bound state in my system. I could even have a third one and so forth. But it's not like the scattering states are going away. Those two particles there are also positive energy solutions. Is that better?
Yeah, yeah. When you were explaining my question, I understand that I'm missing up the all thing in my head because I thinking about three particles and no three bound states. I just lost
Oh,
myself.
okay. No. This is just two bodies
Yeah,
and
yeah, yeah. But
no, but
it's a
your
lot more
question
clear now.
No, but your question is really good because again, I keep coming to the hydrogen atom because I think it's the closest thing to those types of calculations that I'm showing in this course that everybody's familiar with. In the hydrogen atom, since Coulomb has an infinite range, you get an infinite number of bound states, right? There's no finite number of bound states in the hydrogen atom. Of course, at some point, the quantum number n of the hydrogen atom gets so high that you're practically at zero energy, right? So close to the scattering states. But here is not the case. Here I'm talking about potentials that have a finite range and a very short range. So that's the consequence. If they're not attractive enough, I don't even have a single bound state between those two particles. So thank you for the question.
Thanks. Thanks.
More questions, everyone, or is that clear? Okay, so continuing. All right, so far I talked about this spherically symmetric well, but just about the scattering length. We also have to compute the effective range, right? I got away without calculating the normalization of the wave function because in the previous calculations, I always did the first derivative divided by the function, so the normalization constant dropped out. But now for the effective range, I do have to match everything. But it's not hard. You'll see that we just have to equate these two solutions at the range of the potential. Okay, so I get normalization constant here. So that's the normalized solution. And then I have to take the zero energy limit to see how is the wave function in the zero energy limit. So it's this expression that I wrote down at the bottom of the slide. Remember that outside of the range of the potential, regardless of the potential that I choose, it's always going to be 1 minus r over a. Okay. And then I just have to do one integral here that we can do analytically. And I'm writing this, the result of this integral here. I invite you again to do those calculations much more slowly than what I'm doing here, but to see at least once what kind of calculations are involved. But it's just doing that integral. So now I have an expression of the effective range in terms of the parameters of the potential. If I plot this expression here, what do I see? I see that also because I also have those types of tangent behaviors here. This is going to diverge for some values. But in this graph here, I marked with this vertical dashed lines the positions where a bound state appears, or in other words, the positions here where the scattering length is diverging. And the interesting thing to see is that at those positions, the effective range and the range of the potential are equal. So the ratio is 1. So here, here, here. So for the spherical well, the range of my potential, capital R, and the effective range, this R naught here, they're only equal when I have an infinite scattering length. Otherwise, they can be quite different, as you see. They can vary orders of magnitude. So that's an important result. So we really should, in this low energy theory, think about the effective range, not the range of the potential, because the two things can be quite different. So the effective range is the thing that has meaning as a range of the potential. That's why it's called effective range, because it's truly the range that matters in this low energy theory, not the range of the potential per se. Is that result clear to everyone? Yes, no, maybe? I need some feedback. It's clear.
Okay.
Thank you, Paul. Rafael, why is it negative? I'm just so it's just the result of this analytical expression. I mean, this is not. If I told you that. If I told you that the range of a potential was negative, you would say I'm crazy, right? And you should, because the range of a potential should always be a positive number. But the effective range is a term in that expansion. Remember that we had something like R naught k squared over 2, right? So I had this, right, in that expansion. So when it's negative, it's just really saying that this plus here should be a minus. Is that okay, Rafael? Okay. So as I said, it's not like the real range of the potential. It's the range that matters for this low energy theory. Okay. All right. So we saw how the scattering length was related to the bound state energy, but we didn't look at what happened when we include the effective range in those bound state energies. So that's what I want to do in the following. And I want to relate that to some physical systems, so you get a feeling of how good are these approximations that we are talking about. Okay. So a few slides ago, I identified when there's a bound state, that's the kappa of that bound state was 1 over A. So if we have a two-body bound state, remember that when we had two bodies to relate to the results that we derived before, we had to plug in the reduced mass, right? So what we get this simple expression here for the two-body bound state energy, okay? So this is in agreement with what I showed before in that other slide, because every time that the scattering length is infinite, what happens to the bind state energy is 0. So when the bind state first appears, it has 0 energy. As we increase the attraction, this gets more bound as it goes, right? But that's the main result here, that for a 0 range, the energy of my two-body bound system is just related to 1 over A squared. What happens if we want to consider the effective range? So we want to get the bind state energy not as a function of just the scattering length, but also the effective range. Well, we have to look at the pole of the S matrix element that I showed before. And how can we do that? We know the relation between the S matrix and the scattering amplitude. We know that the scattering amplitude has that k cotanus of the phase shift, and that we know that we can replace by -1/A and the effective range over here, all right? So it's just plugging in everything in the expressions that I had before. If I do that, what do I get? I get this expression for the S matrix here, and we know that the bound state corresponds to a pole of this S matrix. So I really should look at the denominator here and look for the pole of this denominator. If I do that, I realize that I need to solve this. This is where the pole of the S matrix is. And this is a quadratic equation in kappa, which has, of course, is a quadratic equation. It has two solutions. So those are the two solutions for that second order equation that I have here in this slide. Two solutions. One of them is physical, the other one is not. So how can I see the one that's physical and the other that's not? Well, I can ask myself what happens when the effective range is small compared to the effective range. So this quantity is small. And then I can expand the square root here. And the result is that I get that kappa R naught here is either 1 minus 1, that's 0, plus R naught over A, meaning that if I choose the upper sign, I get that kappa equals 1 over A, which is the result that I had before. Otherwise, if I chose the inappropriate solution, which is the one with the bottom sign here, I get, what do I get? I get 2 plus R naught over A, which is not the result that we had before. So this is the inappropriate solution. I choose the appropriate one. And then if I do that, I can compute the energy of my bound state as a function of both the scattering length, see that the scattering length appears here, but also the effective range. The effective range appears in this expression. So it's an expression that relates the bound state energy to those two quantities, all right? Before we only had an expression that related to the scattering. I'm going to apply this to a real world problem, like the next slide. But do you get the idea behind that? Is it clear, the idea?
Yes.
Good. All right.
So just a quick question. What is
Sure.
the difference between zero range and finite range?
That's just the names that I'm giving when I write that expression. So when I stop here, if I just write this, I'm calling it zero range, okay? And when I'm putting this next term, I'm calling finite range.
Okay, thanks.
Okay, great. More questions? Okay. So now that I have those two expressions, I can apply them to a physical system, okay? Suppose that I get a potential from the literature, I'm not showing here how it looks like, that describes helium-helium interactions. So helium-4, so I have two helium-4 atoms, and they're interacting through some potential, okay? I get this complicated potential that's in the literature, and I solve the Schrodinger equation, like the full Schrodinger equation, and then I get that the solution, the dimer energy, is this number here, 1.62 millikelvin, okay? Now I get the same potential and I calculate the scattering length and the effective range of this potential, okay? I'm not showing how I did this, but if you believe me, I took the same potential that gives this number here, this bound state energy here, and I solved in the zero energy limit the equation, and then I got the scattering length and the effective range, right? So if I do the zero range approximation, what's the zero range approximation? It's the one that depended only on the scattering length. What's the bind state energy that I get? I get this one, minus 1.48 millikelvin, okay? So let's compare the two values. So the full Schrödinger equation gave this one over here, and this one gave me one that's correct within 8%. So I get 92% of the correct result. So let's pause for a second and digest this result. I didn't solve the full Schrödinger equation, which is an eigenvector eigenvalue problem. I didn't get all the eigenstates. The only thing that I did was I took the potential and solved a simpler equation, which is the Schrödinger equation in the zero range limit. I got this number, which was the scattering length. And then I just did 1 over this number squared, and I got a result that was within 8% of the correct one. So this is a very powerful result with much less work and in a much more simpler setting. I almost got the right answer. Now let's imagine that I went one step beyond and I calculated the effective range of this potential. And then I plugged in this result in that equation that we derived in the last slide that depended on the effective range and the scattering length. And if I do that, I get a result that's within 1% of the correct result. Again, just calculating a number from those zero energy wave functions. So this theory is pretty good in describing this helium dimer, because if I compute what's the typical momentum times the range of the potential, that's of order of 0.1. So this is why this works so well in this situation. Do you understand what I did? Any questions? I need someone talking to me. Okay, Rafael says it's okay. All right, so this was atomic physics. So I'm talking about things in the angstrom scale, that's 10 to the minus 10. I'm talking about energies of order of millikelvin. Now, let's do an example in nuclear physics. Let's look at the deuteron. So the deuteron is the bound state of a proton and a neutron. Here, I'm going to consider the deuteron as if it were just an S-wave interaction. So I'm not going to consider, because the deuteron has a quadrupole moment, so to describe it, I would need to consider L equal to partial wave. But here I'm going to take a simplified approach to the deuteron and consider that it's only a proton and a neutron interacting through S-wave L equals 0 potential, okay? So that's simplification that I'm doing, but you'll see it works well in this case. So the binding energy of the deuteron is this one, so it's in the MeV scale. And then I can get the numbers from the scattering length and effective range of the deuteron. Now I'm going to do the same thing that I did in the last slide. I'm first going to consider only the expression for the bind state energy that considers the scattering length. If I do that, I don't get a very good result, as you see. I'm getting 65, 64% of the correct result. Remember that in the last slide, when I did that for the helium dimer, I got more than 90%. Now, what I really have to do is to go one step more and consider the effective range. Now, if I use the expression that has the effective range, then I can get the correct bound state energy for the deuterium. So why was it that the first result was so good in the case of the helium dimer, and in this one is not that great? It's because for the helium dimer, the product of Kr, it was of order of 10%, and here it's of order of 40%. So that's a very different potential. The range of the potential is much larger in this case. But still, if we consider the effective range, we can match those things, okay? So what's nice about comparing those two results is that they really emphasize how universal this low energy theory is. We were talking about atomic physics in the previous example. Here we're talking about nuclear physics. So 10 to the minus 10 meters and energies of the order of milli electron volts. That should be here. And for nuclear physics, we're talking about femtometers, 10 to the minus 15, and energies of a few MeV, so 10 to the 6 electron volts. So I could have brought examples from particle physics, but I just wanted to show you with those examples how universal these things are. Did I convince you that this is very interesting, useful, and universal?
Yes, it's really very good.
Okay, good.
Yes, you got me too.
Great, great. All right. Let's see. The next topic that I want to talk to you about is how to obtain, giving a potential, how to obtain the scattering length and effective range, like in practice, like numerically, because for most potentials, we cannot do the same thing that we did for the spherical well, that's, doing things analytically. And also the other way around. I have some potential, like the spherical well, and I want to tune my potential to reproduce some scattering length and effective range. Suppose that I want to see, I want to model the deuterium or the helium dimer as a spherical well. So I have the potential, the parameters of my potential, and I have to change them to reproduce the scattering length and the effective range that I know from the literature or for experimental observation, so on. So
But-
how can I do that? Huh?
Sorry.
Sorry?
In
Yes.
fact, I have a question
Sure.
that pops me up. When in the context of the scattering, when we go out the low energy, so we are considering the elastic collisions.
Yes.
We are taking a lot of considerations of our physical system,
Yes.
and in the several fields of applications, atomic physics, nuclear physics, particle physics, what's the same idea that go out of low energy that depends on the each field?
Well, you can see where you start to leave the validity regime of this theory, even in these examples that I'm showing here. If you are doing just a helium dimer, you could do a zero range theory and you would get pretty good results. Of course, that going one step beyond, you get much better. If you do that for the deuterium here, you see that the zero range theory is bad, but if you go a little bit further, it gets better, right? And And as I argued, it's because of the product of this quantity that yesterday when I said, oh, what's the low energy limit? We had several arguments to come to the conclusion that's when this is small, right? So of course, I'm only showing the cases where this work. I'm not showing the cases where some physical system that this is bad and this is bad as well, okay? So has some regime of validity. It doesn't work for all energies, but still many physical systems that are interesting, that are relevant, are described by this theory here. Now, going beyond low energy, do you have a scattering length and effective range? No, you don't, because those two quantities by definition were obtained using the zero energy solution. So you have to take different approaches. Here, I'm trying to focus one that, as you said, has lots of assumptions. But even though it has lots of assumptions, it has applications to lots of systems. So it's not like I'm doing lots of assumptions and I end up describing just one physical system. No, we can do much better than that. Is that better?
Yeah, yes, it's very nice. It's very great. Thanks. Thanks a lot.
Okay. More questions? Okay, so the next topic that I want to talk about is this one. So how we compute, like actually with actual examples, how we compute those scattering lengths and effective ranges numerically. I think it's best if we leave this topic for tomorrow, and then tomorrow I can walk you through what you need to do. Okay? Any more questions? So if no more questions and comments, we can meet again tomorrow at 11.
Okay,
All right?
great. Just send the,
Oh, the slides. Yes.
Yeah.
Thanks for everyone. Yeah.
all right. Thank you. See you
All
tomorrow.
right. See you. Bye-bye.
Bye-bye.
Bye guys, see you tomorrow.